All right, everyone. We're going to do our first lesson here on oxidation states. So this is concept B5 in um, your um, electrochemistry unit, and we are going to start to work through something called oxidation numbers. But before we do that, it would probably be a good idea for you to have a look back at, it's been a little while, some of the stuff we've done already in the unit. In particular, I want you guys to really make sure you're paying attention to Leo goes Gur, not only memorizing what that means, but also understanding what it means, really getting deep into that, and then also having a look at the thing we talked about before as well, which was the strongest oxidizing agent gets reduced. So the SOA gets reduced, and then the strongest reducing agent, this is really hard to do on my laptop, strongest reducing agent, it gets oxidized. Okay, so remember what those things mean, and understand a little bit about what they're all about. Our goal in this concept is going to be continuing to work with oxidizing and reducing agents, but we're going to start to work with this thing called an oxidation number, and we'll define what that is shortly. And I think you're going to find that it's actually relatively simple to work with, and it really is going to help you to see oxidation and reduction occurring in reactions when it's not completely obvious that an oxidation or a reduction is occurring. So we'll fiddle around with that a little bit. We're going to still continue to talk about redox reactions and electron transfer as we have all the way through, and we're going to continue to write balanced equations for redox reactions in acidic and neutral solutions. We've done these first two already, but I want to show you guys how to do oxidation numbers and how to balance using oxidation numbers. So we're going to get into that shortly. So moving on, an oxidation number is I think a really valuable tool, and once you guys master this, it's very, very simple to work with an oxidation number to determine whether an entity has changed or undergone reduction or oxidation in a chemical reaction. So an oxidation number is the relative charge, oops, go back here, the relative charge of each atom in a reaction, or entity in a atoms in this case in a reaction. The numbers for a redox, for an oxidation number can be positive, negative, zero, even decimals or fractions, depending on how you want to work with it. But some simple rules make it possible to identify these oxidation numbers very, very quickly and allow us to work with oxidation numbers in multiple scenarios. So let's explore what these oxidation numbers are. And what you have here is a set of rules associated with oxidation numbers. And I'm not gonna make the I think I might make the camera disappear. Well, maybe I can't. A set of rules to work your way through to determine the oxidation number of an atom. And there's 6 rules up here, but really there's only a few of them that we're going to use super regularly, and so let's just sort of bear in mind that we're not going to use all of these all the time, every single time, and in fact a couple of them I haven't really seen pop up on a diploma exam before. So the first thing to remember is the oxidation number of any atom is always 0. Okay, so in an element it has, so if it's existing by itself outside of a compound, so in its elemental form, its oxidation number is 0, always, no questions asked. Okay, the second thing we need to bear in mind is that the total sum of all oxidation numbers in a molecule equals 0. Okay, so for example, if we had water, which is H2O, its oxidation, if we added all of the oxidation numbers up in water, its oxidation or the sum of all of those will equal 0. Water doesn't have a charge to it, so its oxidation numbers total to 0. Anything in group 1A has an oxidation number of positive 1. Okay, then this one is one of our most important. Hydrogen, in any form except for the exception below, will have an oxidation number of positive 1 when it's part of a compound. If it's bonded to a metal, it will be negative 1. So let's say it's part of a hydride like lithium hydride or sodium hydride, then those lithium or sodiums will be a positive 1 for their oxidation number, and the hydrogen will be a negative 1. But usually, I would say 95% of the time or greater, hydrogen, when it's part of a compound, has an oxidation number of positive 1. Next, oxygen atoms, which we're going to encounter frequently as we move forward. The oxygen atoms that are part of compounds have an oxidation number of 2. Okay, and there are exceptions to this, and like I said, this is one of those cases where we've got these exceptions up here, but to be perfectly honest, I've never seen them come up. So the first exception is for peroxides. If oxygen is bonded to hydrogen in a peroxide, then the oxidation number for oxygen is negative 1 in this case. I've never seen it pop up. It's not going to pop up on my test, but I want to make you aware of it just in case there's a scenario where it does for some reason pop up on the diploma exam this year. And then the other exception to this, usually it's negative 2 for oxygen, but the other exception is if it's bonded with fluorine. Because of the extreme electronegativity of fluorine, oxygen actually ends up with one of its electrons being wrestled away or spending more time over in the fluorine side of the bond, and so we would end up with an oxidation number of +1 for oxygen. The last one, and the one that a lot of people tend to forget, is this one here. If you are dealing with an ion of some sort, and often we're going to end up with, when we're dissociating something, maybe we end up with something like, I can't draw SO4, SO4 2- as an ion. Recognize that whatever the charge of that ion is what the oxidation numbers of the elements in that ion add up to. And I'm going to show some examples in a second here that will illustrate that, I think, a little more clearly for you as we move forward. So just in summary on this slide, the most important rules I believe that you need to commit to memory right away are 1, 2, 3, 4, particularly the first part here where hydrogen is +1, 5, but only really this first part, A and B, recognize them, but I don't think it's going to be super important, and then 6. So there's some things we can ignore in this section if we want to make life a little bit easier. So I'm going to move this back up to the side here, and we'll switch to the next slide, and let's do some examples, and I'll show you how we work through some of this. So if we want to determine the oxidation number, when we're doing this, when we're dealing with a particular compound or a redox reaction, and we're trying to figure out what's being oxidized and what's being reduced, we're going to assign oxidation numbers to each of the atoms in that reaction, and then we're going to be searching to see if those oxidation numbers change between reactants and products. So we're going to get in the habit then of assigning oxidation numbers to each atom in the chemicals. So the example that we have here is Cr2O72-. This is the dichromate ion, and the dichromate ion is an ion. So we're going to invoke one of the rules up here that we talked about, which was the total number of oxidation number in an ion is the same as the charge of the whole ion. And so when we're dealing with dichromate, we know that all of the oxidation numbers in here are going to add up to equal -2. So here's how I would do this. It's really simple algebra that we're going to be doing here. what is unknown to us right now is what the oxidation number of chromium is in this particular ion. And maybe that's something I should have mentioned before, is certain atoms can have different oxidation numbers depending on the situation we're putting those atoms into. So chromium is part of the dichromate ion here. That means it's going to have a particular oxidation number when it is part of this ion right here. However, if we put chromium as part of chromate instead of dichromate, its oxidation number will be different. Carbon is a good example of this. If it's part of propane, it's going to have a particular oxidation number. If it's part of glucose, it's going to have a different oxidation number. So you'll have to sort of figure it out on a case-by-case basis. So it's really easy for us right now to simply say that oxygen has a -2 oxidation number. Because it's oxygen, it's not in its elemental form, so it's not going to have a 0 oxidation number. It's not part of a peroxide, it's not bonded to fluorine, so it's going to have an oxidation number of -2. So what I would suggest at this point is we're not sure what chromium's oxidation number is going to be. So we can just set up a simple algebraic expression to solve for this. So there are two chromiums, in this. So I'm going to say that there are two x's in this expression that we're setting up. And then we know that if we add all of the oxidation numbers together in this ion, it should equal -2. So this is going to equal -2. Okay. And then we just have to take care of oxygen here. So we're going to add that. There are 7 oxygens, with each of them having an oxidation number of -2. And I apologize for the drawing. When I get home and I'm working on my computer at home, it'll be a little bit better quality, I think, when it comes out here. So 2x plus 7 times -2 equals -2. So we can simplify this for those of you that are not as comfortable with algebra, and I am one of those people. I like to do things in full. This is 2x minus 14 equals -2. This is painful to draw on a trackpad. And so then if we finally get down to simplifying this, 2x then equals positive 12, okay, because we bring the negative over, and x then is going to equal 6. So our oxidation number for chromium is positive 6. And I think it's important for you guys at this point to start to use positives and negatives if you aren't already, because it's going to allow you to really detect whether something has gone through oxidation or reduction. If it goes from, let's say, a positive to a negative, that means it's getting more negative. If it's getting more negative, then that means that it is being reduced because it's gaining electrons. Electrons are negative, right? If it's gone from negative to positive or negative to 0, then you know that that entity is getting oxidized because it's losing electrons. Losing electrons means you get more positive because electrons are negative. Okay, so what I'm going to do here is we're just going to go through a couple of examples and sort of sort our way through them, and then I'm going to sort of hit pause, I think, and get you guys to do some practice on one of the worksheets, or you can hit pause and do some practice on one of the worksheets. So I'll continue to draw here as we move through. So copper, solid by itself, element all by itself, that's rule number 1. It's going to have an oxidation number of 0. Okay, I don't like that writing tool. We'll go back to the other one. The next one, water. Okay, so we said this has an oxidation number of 0 because it's an element all by itself. The next one is water. So this is going to combine a bunch of rules. Oops. It's going to combine, it's going to combine rules 2, 4, and 5 in this case. So we're going to be dealing with rule 2, which says that in a molecule like this, everything, when we add up those oxidation numbers, has to equal 0. Okay. The next thing that we're going to see is we're dealing with hydrogen as part of a compound, okay, and we're dealing with oxygen as part of a compound. And so if we look at this, and this will make logical sense, if we have two plus 1s, that's plus 2, and a minus 2, that's going to give us a total of 0. Okay, so our oxidation numbers in water, our hydrogen is going to be plus 1, oxygen is going to be minus 2. That's fairly straightforward. I'm going to jump over here to E. This is rule number 6 we talked about. This is an ion, and whatever its charge is indicates the overall charge for this particular ion. So I would kind of look at this, if we want to stay true to what number 6 is saying. Our charge is plus 1 on this, and so X is equal to plus 1. There's only one copper here, so it's going to be our X is equal to plus 1 in this case. I'm going to jump to methane down here. Hydrogen, part of a compound, has an oxidation number of plus 1. So then what is the oxidation number for carbon in this case? Well, it's going to be X plus 4 times, because there's 4 hydrogens, 4 times plus 1. Okay, and then because this is a molecule, it's all going to total 0. So our oxidation number for carbon in this case is going to be negative 4. Okay, because it all has to add up to 0. Okay, I just went and switched to grab a mouse instead of the trackpad so I can make this a little bit easier. Let's move on to D then. Same kind of situation here. We're going to indicate that the oxidation number for hydrogen in this case is plus 1, same as it's been in the last few examples. But we're unsure of what the oxidation number for carbon is going to be. So let's set up our simple algebraic equation, right? 3x. Okay, carbon is the one we're not sure of, so we'll assign it X. There's 3 carbons, plus 8 times plus 1, okay, because there are 8 hydrogens and it has an oxidation number of plus 1, equals, and then we need to sort out the fact that this is a molecule, so it's going to total 0. Okay, then you just work your way through the algebra, right? 3x equals minus 8. I basically just turned this into 8 and moved it over to the other side. So x is equal to negative 8 over 3. And it's fine to leave it as a fraction in that case. So our oxidation number for carbon here is negative 8 over 3. Remember, don't throw away the negatives. You're going to need those negatives as you move forward. Let's jump up to sulfate ion here. So same kind of idea, right? Oxygen, part of a compound or an ion, unless it's a peroxide or paired with fluorine, it's going to be minus 2. Sulfur we don't know, so we'll assign it to be X. So this is going to be X plus 4 times minus 2, okay, equals negative 2. Okay, so this is going to be X minus 8 equals negative 2, so X is equal to 6 in this case. Okay, so this becomes an oxidation number of positive 6. Okay, this one again we can still fiddle around with, right? Oxygen and hydrogen. Oxygen, part of a compound, is minus 2. Hydrogen, part of a compound, is plus 1. And so we're just going to do X, because there's only one of them, plus 2, I shouldn't have put that bracket there, 2 times plus 1, plus negative 2, and this is all going to equal 0 in this case. And so you'll work out your algebra. This negative 2 comes over, becomes positive. This one becomes negative. We're actually going to see that this is going to equal 0 for its oxidation number. Okay, so I think that's probably enough examples for you guys at this point. What we're going to do is I'm going to get you, at this point, I've introduced to you what oxidation numbers are. I had to jump off there, and all of my work disappeared off here. But you can go back a couple of seconds if you need to go and have a look at it again. But what I'd like you guys to do now is hit pause on this, and then go to your package of worksheets and look for LSM 13.3b and get to work on it. It's going to give you some practice on identifying oxidation numbers in these first two questions here, and you can see we're working through manganese in lots of different forms on this one. And then the second thing, when you get down to questions 3, 4, 5, 6, 7, etc., is what they're asking you to do is fill out oxidation numbers for these. We're not balancing the equations at this point, but what you're going to do is you're going to fill out the oxidation numbers and then determine if something is being oxidized or reduced, which atom is being oxidized, which atom is being reduced. And you're going to be checking to see the difference in oxidation numbers between the reactants and products. So it might be that astatine is getting oxidized and iodine is getting reduced. Remember, oxidation means loss of electrons. So you're losing electrons, meaning you're getting more positive. Reduction means gain of electrons, so it means you're gaining electrons and getting more negative. So if your oxidation number becomes more negative, you're being reduced. If your oxidation number becomes more positive, you're being oxidized. Okay, so I would encourage you to hit pause now and do some practice with that. Don't forget the keys in the Google Classroom. Check your answers. Get a hold of me if you're not sure what's going on. And then I'm going to move on to talking about the next section, which is balancing using these oxidation numbers. Okay, so hopefully the working through oxidation numbers worked out well for you. If it didn't, make sure you get a hold of me. But where I'm moving on to now then is I want to talk about how we can use oxidation numbers to balance a chemical equation or a redox reaction. And we're going to be using what you just did on that worksheet, that identifying whether an entity is being oxidized or reduced, in order to be able to do this. And we're going to follow again a little bit of a procedure to work our way through this. And this procedure is rather important for us to work our way through. And I'm just going to highlight it right now, and then I'm going to bring up, I believe I've got an example that we'll work through together. I'll show you how to work through it, and I'm actually going to do it written out instead of me drawing on the screen here, because it's just not going to work so well. So I'll work my way through that in a minute here, and maybe add it to this video. So the rules for this is that oxidation numbers we just learned, help us determine what's being oxidized and what's being reduced. And so once we can do that, we can actually do a quick balancing using these oxidation numbers. So what I'm going to do and what I'm going to show you guys is above each item or atom in the reaction, you're going to write the oxidation number per atom of the molecule. And the atom of the reactants which has its oxidation number increase, meaning it becomes more positive, is going to be the atom that is getting oxidized, and the atom that has its oxidation number get smaller or more negative is going to be reduced. That's why we should call this unit a redox reaction or redox unit, because that's really what it all is about: reduction and oxidation. So that's I guess just a bit of a summary of what I was wanting you guys to work on that last worksheet. I can probably work through this one quickly using my mouse, and then we won't have to re-record everything. We figured out propane in this example up here. So if you recall, propane had a negative 8/3 for its oxidation number. Hydrogen was +1. Oxygen in its elemental form, all by itself here, any element all by itself is going to be an oxidation number of 0. I like to do the easy ones first, right? Oxygen is -2. Hydrogen is +1. Oxygen is -2 again here. So now we just have to figure out what carbon is. Well, if there's 2 of these -2s, that's -4. We've got 1 carbon to balance things out, so carbon has to be a +4 here. Okay, so we filled in all of our oxidation numbers. I'm just going to switch colors here to maybe white so we can see it better. I'm looking and seeing hydrogen on this side and hydrogen on this side. Those are both +1. So if the oxidation numbers are exactly the same, there is no oxidation or reduction taking place. So hydrogen is spectating in this reaction. But look at oxygen. Oxygen went from 0 here to -2 on both sides. So if it went from 0 to -2, like we see here, it has gotten more negative. Okay, if you get more negative, that means you're gaining electrons. If you're gaining electrons, that has to be reduction. So oxygen got reduced. Carbon, on the other hand, if you look, it went from -8/3 to +4. So it is obviously, I'm just going to switch colors to make this stand out a little bit better. With yellow. It is obviously gone to become more positive. If you become more positive, that's oxidation. And so what is being oxidized in this reaction? Well, carbon is being oxidized, oxygen is being reduced, so we have a redox reaction in this case. This is another example here of how we would do this. Again, you would have done this on that worksheet previously. You can write out the balanced equation of this and start to work it out. So natural gas burns. So natural gas is methane, and it's burning. Well, burning is combustion, and it's going to produce carbon dioxide. It says CO2, and it's going to produce water. And because it's burning, we'll assume it produces gaseous water, which is something we learned back in the previous unit. And then to sort this out, we should probably make sure we balance, because that's always good practice to be in. So we need a 2 in front of there and a 2 in front of there. And I'm going to switch colors here and switch to white, and we'll fill in our oxidation numbers. So oxygen, again, no charge because it's an element, but it's going to be -2 over here and -2 over here. Hydrogen is going to be +1. There's carbon dioxide again, so that must mean it's +4 when carbon is part of carbon dioxide. Hydrogen here is +1 again, and if we have 4 positives, that must mean that carbon here is -4. So we've got all of our oxidation numbers figured out. It should be pretty obvious again that oxygen here is going through reduction, correct? Because it's becoming more negative. Becoming more negative means you're gaining electrons. Gain of electrons is reduction. And then switch to yellow again. For hydrogen, it's not changing at all. +1, +1 for its oxidation numbers. But we can see that carbon here has gone from -4 to +4. So it's gotten more positive. More positive means you've lost electrons. Loss of electrons is oxidation. So carbon has been oxidized. Okay? Now we're going to jump into this whole balancing thing. So in summary, according to current theory, a redox reaction is a chemical reaction in which electrons are transferred and oxidation numbers change. Oxidation is the increase in oxidation number and corresponds to a loss of electrons. Reduction is the decrease in oxidation number, which corresponds to a gain of electrons. So now, after I goofed up before, this is where we're going to get into balancing equations using oxidation numbers. It's again, you have to be able to establish the oxidation number for each atom in the reactants and the products, and that's going to allow you to determine whether something's being oxidized or reduced, and we can go from there. So to this point, most reactions we've had deal with easy to balance, have been easy to balance. Single replacement, combustion reactions, even some of those ones taking place in solution have been fairly easy. But there are more complex reactions out there that can actually probably be easier balanced using a oxidation number method. In fact, there's some balancing equations that we've done in worksheets in Science 10 that I actually would balance using oxidation numbers, because it's way faster than the tools that I taught you guys in Science 10, believe it or not. Oxidation numbers and half reactions can greatly aid us in balancing equations, and assigning oxidation numbers to each atom or ion in a reaction allows us to determine if the reaction is a redox reaction or not. That is a little key tidbit right there. This little bit right here, and I'll put a very poorly drawn star beside it. This is important because you can actually use oxidation numbers as a tool to determine if a reaction is oxidation or reduction, sorry, to determine if a reaction is redox or not. And quite often there's a diploma question out there where they'll say, determine which of the reactions is a redox or which one is not a redox. And so what you would do is go through A, B, C, D, and you would fill in oxidation numbers for each atom in that redox reaction. And what you should be able to see very obviously is that there will be one reaction where none of the oxidation numbers change. That is your reaction that is not a redox reaction. Here's a hint. Usually it's a double replacement reaction. I'm not going to say always, but usually it's a double replacement reaction that is not a redox reaction. We have to remember that the total number of electrons lost by one atom or ion must equal the total number of electrons gained by another. That's electron transfer theory. We talked about that back in D1. And that the total increase in oxidation number for a particular atom or ion must equal the decrease in oxidation number. Okay, so we're going to work on balancing using those principles. So here's another 5 to 7 step method that we talked about back in B2. If you guys recall, we did a 5 or 7 step. This is another one very similar to what we talked about in concept B2. And we're going to work through this example. And this is where I think I'm going to splice in a different recording using my iPad to show you guys how to work through one of these examples. But the procedure you're going to follow is you're going to assign oxidation numbers and identify the atoms or ions whose oxidation numbers change. You'll use the change in oxidation numbers to write the number of electrons transferred per atom. And then, so it's going to be per atom that you'll do first, and then it will be using per chemical entity, so whether it's a molecule or an ion or something like that afterwards. So that's step 3 is using chemical formulas to determine the number of electrons transferred per reactant, and then we'll calculate the simplest whole number coefficient that will balance the electrons transferred. And then what's not completely obvious on here, you can't quite see the bottom, is that we will balance oxygens using water, again like we did in concept B2, and balancing hydrogen using hydrogen ions, like we did in B2, if it's an acidic solution. If it's a basic solution, then we do that little bit with OHs again, and we'll do an example of that here shortly. Okay, so I'm going to try to do some an example of this. It didn't work on the iPad, so I'm going to try it this way with you guys on the whiteboard here. Temporary solution until I can figure stuff out at home, I think. But so your example 1 is what we're working on, and I'm going to make the video larger here for you so you can have a better chance of seeing what's over my shoulder. So in this case, we've got hydrogen sulfide gas reacting with oxygen to produce sulfur dioxide. And we're going to use our oxidation numbers to do the balancing here. And the first thing that we have to do is we need to, I'm just going to shift the camera a little bit so I've got lots of room to write, and if I need to tilt it a bit I can. What we need to do is write in oxidation numbers above everything. So I'm going to fill in oxidation numbers. I hope you guys can see them up there. Hydrogen sulfide is +1. Oxygen in its elemental form is going to be 0. Oxygen over here is going to be -2 because it's no longer in its elemental form, it's part of a compound. Hydrogen here will be +1, oxygen will be -2. And then the thing that we're not 100% sure of right now is our sulfur dioxide, our hydrogen sulfide. So we can just set up our equation, X for sulfur +2 times +1 equals 0. So in this case, this is X + 2 equals 0. So X is going to equal -2. So sulfur here has an oxidation number of -2. I'm going to erase this, but if you need to go back in the video to find it again, you certainly can. What we can do now is we can identify, that was basically we're going to finish off step 1. What are the things that are changing? Well, hydrogen is not changing. Its oxidation numbers are remaining constant. Sulfur went from -2, oh, sorry, we got to do it on this side yet. It's going to be +4 over here. So it went from -2 to +4 over on this side. So it is being oxidized. So this looks like an oxidation. And then oxygen went from 0 to -2. So it has gotten reduced. Okay, so that's our steps there. Hopefully this is going to be big enough for you guys to see. I can try to write a little larger. What we have to do now is we have to move on to the next steps, which are suggesting that we work our way through the number of electrons these things have changed by. So let's look at sulfur first. It went from -2 to +4. -2 to +4 is a difference of 6 electrons, right? 6 electrons per sulfur. Oxygen over here went from 0 to -2. So per oxygen atom, that's a difference of 2 electrons per oxygen atom. Hopefully that makes sense to you. The next bit here then is we need to look at the whole. So we just looked at sulfur itself and oxygen itself. We need to look at the whole entity that it's part of. So sulfur, there's one of them here. So we can say that that is a transfer of 6 electrons per H2S. However, for oxygen, oxygen has 2 in it. So there's 2 oxygens in here. So we are going to say that if it's 2 electrons per oxygen atom, and there are 2 atoms here, that must mean there are 4 electrons transferred per oxygen molecule. Okay? Then the last step, or the next step in here, is to look and see if these numbers here are equal, and they're not. We've had 6 electrons transferred here and 4 electrons transferred here. The number of electrons lost must equal the number of electrons gained. And so what we need to do here is use whole number coefficients to ensure that the number of electrons lost and gained are equal. And so we're going to multiply this by 3 and this by 2 in order to make sure that that happens, right? Because 2 times 6 is 12 and 3 times 4 is 12. So that what this 2 represents then is a coefficient of 2 up here. And what this 3 represents is a coefficient of 3 up here. What this also does then is make the fact that there are 2 H2S's here mean that there are 2 sulfurs on this side, but there's only 1 sulfur on this side. So we need a 2 for the coefficient up there. And then the other thing we want to do at this point is just double check that we've balanced other things correctly, and I can see right now we haven't. It looks like our sulfurs are good, 2 sulfurs on this side, 2 sulfurs on this side. However, 4 hydrogens over here and only 2 over here. So that's going to require a coefficient of 2 in front of the water. And then oxygens, I see 3 times 2 is 6 here. There's 4 there and another 2 here. So everything appears to be balanced. What we should notice in this example is that it doesn't say anything about being acidic or basic. And so we can really ignore what's going on with the acidity and basicity. Everything is balanced at this point. Key things to watch out for here is if you have a subscript of 2 or more, then that modifies what you said per atom here by whatever this value is. So we took 2 times 2 gave us 4. Basically here we did 1 times 6 gave us 6. Okay, I'm going to hit pause and set up the next question. Okay, so we're going to switch to the next question here. This one's a little bit more complicated because it involves us doing something in a basic solution. And so it's going to take us through steps 6 and 7. If you can do this one, you can balance anything as far as I'm concerned using oxidation numbers. So I'm going to hit pause for a second, write up the equation that's on here on the board, and then we'll start assigning oxidation numbers. Now I've got written up on the board here, and now we're going to go ahead and start to balance like we did before. Hopefully you guys can still see this. I'm going to fill in the simple things first. Hydrogen is going to be +1 because it's part of a compound. Oxygen will be -2 because it's part of a compound, and on this side as well. So right now I'm looking and realizing, well, it doesn't look like oxygen is being oxidized or reduced at all. And it doesn't look, and we don't have any hydrogen over here, which we'll get later on this side when we're dealing with our basic portion of things. But what we do need to figure out are the oxidation numbers for carbon on both sides and for manganese on both sides. I figured these out ahead of time, so I'm going to fill them in. This one is +7. This one is +6. We've got sorry, something's distracting in the background. Alrighty, and so we'll fill in the last pieces here too. This one is going from -2 to +4 for that oxidation number. So carbon is changing, getting more positive, meaning it's being oxidized. Manganese is getting more negative, going from +7 to +6, meaning that it is getting reduced. So let's look at changes in electrons then. From -2 to +4 means that this has lost 6 electrons per carbon atom. The manganese, on the other hand, has gained 1 electron per manganese atom, right? It went from +7 to +6. That's a difference of 1. This is a difference of 6 between those two. Now, there's a coefficient of 1 for the carbon here, so we can say that that's a transfer of 6 electrons per methanol molecule, and we can also say, because there's a coefficient of 1 here, that there's a transfer of 1 electron per manganate ion. So then what we have to do is we have to say, okay, well, if these are the electrons being lost and these are the electrons being gained, how does that work out? What does that work out for us? So if you're losing 6 and gaining 1, that doesn't work out. So we have to modify this one by multiplying by 6 and this one by multiplying by 1 in order to ensure electrons lost equals electrons gained. What this means then is that this 6 becomes the coefficient for the permanganate ion. And so then that also transfers to meaning a 6 for that ion over on the other side here as well. What we can do now is, because we've now balanced everything that is not oxygen and hydrogen, we can move on to our steps that are involving basic and acidic solutions, and we can start by balancing oxygens using water. And we're going to have to keep a little tally going on here because there's a lot of oxygens going on. On the reactant side, there are 24 in these 6 here, plus another 1 is 25. And then over here, we've got another 24 plus 3 is 27. So we've got 27 oxygens on the product side and 25 on the reactant side, meaning that we need to add 2 water molecules to bring this side up to the correct amount of oxygens. Next, we can balance hydrogens using hydrogen ions. There are 4 hydrogens here plus another 4 in this molecule, giving us a total of 8 hydrogens on the reactant side. On the product side, there's no hydrogens. So I'm going to add 8 hydrogens to the reactant side. Shift the camera a little bit so we have a little tiny bit more room on that one side. And what we're going to do now is we're going to move on to step 6 and 7, which is the same as step 6 and 7 that you guys did in concept B2. We're going to add hydroxide ions equal to the number of hydrogen ions that we added in the first place. So there's 8 hydrogen ions here, meaning 8 hydroxide ions are going to get added to both sides. Okay, and then the last step is to take these hydrogen ions here and those hydroxide ions, and we're going to combine them into 8 water molecules. Okay, and then we can cancel out the 2 water molecules that are here and reduce this down to 6. So I'm going to rewrite this so you guys can see the final damage that we had on this. So it's going to be 8OH and CH3OH, and 6MnO4, 1 minus, turns into CO3, 2 minus, 6MnO4, 2 minus, and 6H2O. It's not a bad idea at this point to ensure that your charges are balanced. I've got 8 negatives plus another 6 negatives gives me 14 negatives on this side, and I've got 6 times 2 is 12 negatives plus another 2, which is 14 negatives on this side. So I hope that worked out. I'm going to continue to work on getting a better way to do these examples for you guys to see a little more easily. Example 3 that you have in there, you guys can do on your own. Use your textbook. All of these examples are based out of your textbook. So if you're having trouble seeing what I've done on the whiteboard here in the classroom, maybe go to your textbook and use that as a secondary resource for you. I'm going to pause right now, go back to my desk, and let you know what I need you to finish up next. So I'm back at my desk, and I'm going to get you guys to just remember, go and do example number 3 on your own. Use your textbook because it's out of your textbook to give you an example of what's going on. I'm already at 45 minutes on this recording, so and it's taken me a lot longer to get to that 45 minutes. So what I need you guys to finish up then is you're going to be moving on to do some practice. This is the end of what I have to teach you for B5. So if you haven't already done the worksheet that I assigned in the first section of B5, go and do that, and then you can jump to this right here, which is the next worksheet in your package of worksheets, LSM 13.3E. And you can do that one. That one's going to have you doing just the stuff that we've done on the board and in the last bit using balancing. And then again, the key is on the Google Classroom. And then the only other thing that you could do, I think is a good idea to do right now, is you can get started on worksheet number 2. It goes back to stuff in B2 and B3 as well. So 1 is in B2, 2 is B3, 3 and 4 you would do concept B4 with, and then B5 is question number 4, and you can also do question number 5. I'm not going to tell you how to do that one just yet, but the keys on the Google Classroom. So that was a really choppy first lesson. I'm going to learn a bunch of stuff from this, and I'd like to hear your feedback at some point. If there's anything that you guys need me to change up along the way here, but that is concept B5. You can expect maybe some practice questions up on the Google Classroom as well that you should check out other than the ones I've assigned, and then I'll have a quiz up in the next day or two if you feel like you're ready to do the quiz. Keep an eye open for office hours as well. Best of luck. Get a hold of me if you need any help, and stay healthy.